now we will start with adaptive filtering. First, we should look at that why the adaptive filtering is required. The first scenario is the power line interference with varying power frequency. Let us look at that how our power system is managed. At every instance, we are switching on some light, fan, pump, air conditioner or so many other electrical gadgets. Now, for each one of them that we are changing the demand on the actually power system, and if you look at every instant that the demand is actually the change is a sum total of all these changes, and the generating station actually feeding that power to this system. So, whenever there is a change in demand, that what we find that generator which is producing that power, that it is actually having some reaction to that change. If we try to draw more power, that means we switch on more equipments, then it will put a demand on the generator, but on the other hand the generator is run by a prime mover. Say most of the cases that generating stations are thermal stations. So, let us take the example of a the turbine, steam turbine, which is acting as a prime mover for that thermal power station. Now, there as the demand is more than the power supplied by the prime mover, there would be a deceleration of that rotor of that generator, and that deceleration or the change in RPM, that is actually detected and that is fed to the control system of the prime mover. So, that what we do, we increase the feed there, feed of fuel, so that again the prime mover compensate for that loss of inertia and it feeds actually more energy, so that demand could be met. And if that we keep on switching on the load, that in that case what will happen, that due to the sudden change in the load, that but the prime mover is actually supplying the power at the same rate, the rotor of the generator will start actually moving at a higher speed. That means, it will accelerate. So, to compensate for that, again the control system will detect that change and give a appropriate negative feedback. In that case, that the supply to the prime mover, that should be reduced, so that there is a balance is maintained between the input and output. Now, if we look at these generators, that the part of the prime mover, they are mechanical equipment. So, even if the control circuitry in the side of the generator, that is the electrical equipments or electronic equipments which are having a fast response, the end part of it, when we are actuating the prime mover, that part is slow, and due to that there is a lag in the response. So, because of that we find the power frequency is changing all the time, and as per the law it allows actually 3% in India, that it's allowed 3% actually change, plus minus 3% change. That means, over 50 hertz, plus minus 3% means 1.5 hertz, it can go below that power frequency as well as it can go above the power frequency. Now, under that scenario, what can happen? We have found so far that notch filter is the base to actually take care of the power frequency interference. That notch filter which is designed at 50 hertz say. Now, as the power frequency is changing, that the interference from the power frequency also will change its position and the notch filter will not be effective anymore. So, what to do in this scenario? That the optimal filtering or the notch filtering, it cannot take care of this scenario, which is one of the example that why adaptive filtering is required. Now, let us look at the next scenario, that already we have told about the ECG signal of the fetus and the mother. Now, when the child or the fetus is in the womb, then when we are trying to get the mother's ECG, the fetus ECG added up with the mother ECG and acts as an interference. Sometimes we may be interested to check the health of the fetus, and we would like to take the ECG from the fetus, but in that case also what will happen, even if we put the probe in the abdomen of the mother, because the mother's ECG is stronger, it will again ride on that the fetus ECG and act as an interference there. Now, in such cases, because they are actually the spectrum is very much overlapping, and again both of them they are actually cyclostationary signal, they are changing over the time slowly, that there is no other way other than adaptive filtering to actually remove from each other or separate each other. The third example let us look at, that is the vibro orthogram. We hear about the people, old people who have to go for the knee surgery or knee replacement surgery. Now, the first stage of it, what happens, that the knee joint, which is a hinge, that both the sides of the bones, they are having some cartilages, and that actually is lubricated with some fluid there. So, if it happens that due to some reason, maybe that overweight or some other disease, that degeneration of that cartilage happens and it becomes rough, then the moment you try to actually fold the leg, that means the hinge is operated, there would be a much higher friction, and that gives rise to some noise which could be audible by a microphone. So, that is actually the vibration that is picked from that knee, that is called the vibro orthogram. But as we are moving the knee, there must be some signal given to the muscle, and that the vibration generated by those muscles, that is the vibromyogram, that actually also picked by the the mic there. So, what we find, that while we are interested to know that what is the amount of noise generated by the knee or what is the condition of the vibro orthogram, we are getting another unwanted signal, and both of them they are non-stationary, because they are started, actually their generation started when we started moving the knee, and as soon as the movement is completed, they subside. So, here again our none of the filters what we have read, they are actually could give a good result to separate them. So, now let us look at the new problem statement, that we have already learnt about the optimal filter. So, we do not want to lose on that. That here the problem statement is that we would like to have an optimal filter, but it should work in a non-stationary environment, that means the signal is non-stationary or the interfering noise or interfering signal is non-stationary. In other words, we want an optimal filter, at the same time it should adapt with the time or adapt with the signals it is dealing with. So, that is the motivation for having a adaptive filter in this case. Now, let us look at the structure of the adaptive filter. That first, the application we have taken, it is adaptive noise canceller, and it is interesting enough that here like the previous case, that we have the input x n, that is the observed signal. It is a sum of V n, that is our signal of interest, this is the signal of our interest, and interfering signal or noise is M n here in this case. Okay. And these two, that they should be uncorrelated with each other, and here the other input what we have taken, the reference, it is some signal R n which is correlated with the noise. Now, what is the advantage in taking the signal which is correlated with the noise? I think it is much easier to actually get. For example, if the primary that noise here is the power frequency hum, in that case, that what we can do, we can take the the power line and take the reference, because power frequency hum would be related to the power supply voltage, which we can directly take from that power supply. And then what we can do, this reference input which is correlated with the noise, it can be passed with an adaptive IIR filter, and we can generate something, or rather we can synthesize something called Y n, which is actually would be an estimate of this noise M n. So, if we subtract this one from the observed signal, we expect that we get somewhat closer to that signal of interest or V n. So, here we look at the scenario that we have this error E n. This error is the difference between x n, that is the observed signal, minus the estimate of that noise, which has come synthesized by the adaptive FIR filter and with the help of the reference input. Now, this error we can name that as V tilde n, because we expect that would be close to something of our signal of interest V n, and if we actually replace x n with V n plus M n, we can write it in that way also. So, that is the basic form we get for that desired signal. So, interesting enough here that by changing the reference input to that reference of that noise, that means the correlated signal that with the noise, the output what we call as error, that is actually is coming close to the desired signal of or signal of our interest. So, now let us look at that form more closely. As we know, in case of optimal filter, when we talk about the optimality, we need to tell that what is the sense of optimality, and once again that sense is that we are trying to minimize the mean square error. So, let us look at the expression of the mean square error. So, it is expectation of E square n, and by replacing that E square n by the expression what we got in the previous page, that is V n plus m n minus y n, the whole square of it. Now, we can make it in actually two terms, one part is V n, another part is m n minus y n. So, we can actually expand that the square operation and the square term, and we can get three terms here. Out of them, that one term that is cross between the V n and m n minus y n. On the other hand, the first two terms, they are square of V n and that m n minus y n. Now, this cross term, this is that this one, that V n is uncorrelated with m n, and because y n is correlated with m n, V n is also uncorrelated with y n. So, in this scenario, what will happen, that we can get actually that expression as that expectation of V n into expectation of m n minus y n. Now, as the noise is 0 mean and signal is also 0 mean, both these terms, that means the expected value of them would go to 0. So, these term, the cross term goes to 0, and what we all need is actually uncorrelatedness of the signal and the noise. And please note that there is no more demand on the signal, we do not even ask for the stationarity of the signal. So, with that we can show that the mean square error, it boils down the two terms. One is that we have the energy of the signal and the energy of the difference of the estimate of noise and that estimated noise. Okay. So, that is the expression we get at this point, and let us move forward. Now, when we try to minimize this error or MSE, that expectation of E square n, what we get here actually, that E square n is that we get a term with the first term, we do not actually, if we try to take the minimization, we do not find any effect on that. That the reason is that the minimization is taken by what? We change the tap weights of the FIR filter. Now, that does not have any effect on the standard deviation of the input signal. However, it can change that the estimate y n, and thereby it can change the second term, that m n minus y n. So, that part, when we minimize the error, actually the second term can be minimized, the first term remains unchanged. Okay. And another thing we get that from this, that we are just rearranging the sides, that error minus V n, that is that error is the output of that noise canceller, and V n is the signal of interest. This is equal to Mn minus Yn, Mn is the interfering noise and Yn is the estimate of the noise. So, if we can achieve this, that by minimizing the second term, the minimum value can happen to 0, because we are taking the square, that it cannot be negative. So, the minimum is 0. So, in that case, what we can get, that Mn equal to Yn, that means there is no error there, and as a result of it, because there is no error in the estimation of that noise, then that whatever the output we are getting from the adaptive filter En, that becomes that Vn, or the signal of interest. In other words, actually in this scenario, we are able to get the noise free signal. So, that is actually the goal of our adaptive filter. Now, here we again come back to the adaptive noise canceller structure, and we get that the emphasis will go now to that filter we have taken, that the reference signal Rn, that is fed to a tap delay filter, and for different actually lags, the value of Rn we take and multiply with the tap weights, and we sum them up, which gives rise to our estimate of the noise, that is Yn. And as we subtract that from our observed signal Xn, we get the output En. So, here that Yn is actually sum of the present value of the reference as well as past m minus 1 values of the references, and this Wk is the weight which is actually, if it is properly tuned, it can actually bring Yn close to the interfering additive signal or additive noise, we should say, that is Mn. So, in this case, for this diagram, we get the error is Xn minus Yn, or the difference between the observed signal minus the estimate of the noise. So, this part, the adaptive noise canceller, now we can write into a very compact form, and first what we can do, that we can write the tap weights W, that this one is a m by 1, this one is a m by 1 dimensional vector. And please note one thing, that unlike the optimal filter, here the tap weight is having an index of n, that means it is changing with time, so that it can adapt and give us the optimal input, that optimal estimate of the noise, even if that interfering signal or the signal of interest, they are changing with the time, and maintain that optimality. So, Wn we get as a m by 1 vector, and it will update with time, and that is the difference with the previous Wiener filter. The Xn remains to be the same, it is again m by 1 vector, that, and it is consisting of the present value of Xn as well as the past m minus 1 values. the reference signal for the noise canceller R n, that it is again m by 1 vector, and it is the present and last m minus 1 values, and here the R n is chosen in such a way that it is correlated with the additive interfering noise. And in this scenario, that the output of the noise canceller, that is E n, it is nothing but the difference of the observed signal and the dot product of the weight and that reference input R n. And here couple of things that we should note, that there is no assumptions on V n, M n and R n other than independence of V n and M n and correlation between M n and R n. Actually, independence is a stronger condition. We can say just that they are uncorrelated, that is good enough to show this actually theory or derive this theory. Again, that same set of equations, they can be extended where M n and R n are deterministic, they are not actually random processes. Even in that case, we can actually use this framework or same set of equations and apply the adaptive filter for that better noise cancellation. Now, here we look at that the different kind of adaptive filters. There are two common actually or very popular adaptive filters. One of them is the least mean square algorithm or LMS adaptive filter. The other one is called that recursive least square adaptive filter, or in short we call it RLS adaptive filter. Thank you.